James, the floor is yours. Tell us more about Dask.
Yeah, sure. I'll go ahead and share my screen. Just real quick, Dustin, great presentation, both in terms of content, and that was a awesome format. I was digging the tabs format. That was awesome. So I'm going to assume people can hear me and see my screen. If that's not the case, you can feel free to speak up. In terms of questions, yeah, feel free to just put them kind of same as with Dustin's presentation. Feel free to put them in the chat. And Dylan, if a couple things seem particularly relevant, you can feel free to ask me during the talk. And if not, I'll just go through them at the end. So yeah, hi everyone. My name is James Bourbeau. I'm the lead OSS engineer at Coiled, and I am excited to talk about Dask. Here's a brief outline for the talk. There's actually a ton of content here, these are large topics, and I've kind of stripped them down, and I'm trying to provide sort of links to other community resources for you to go check things out. This is more like kind of a launch pad for further discovery in whatever particular portion you're interested in. So that being said, the first portion of this talk, I'm going to give a high-level overview of Dask itself as a project. And then I'm going to talk a little bit about deploying Dask clusters. And then I'm going to talk specifically about Coiled, deploying Dask clusters with Coiled. This is one particular service for deploying Dask clusters. A little bit about me. My formal education is as a physicist. During my PhD, I spent a lot of time analyzing large data sets from particle detectors. That's actually how I got involved with Dask in the first place. I ended up using Dask in my research to process lots of HDF data sets. Fast forward several years, and I'm actually a core Dask maintainer. And then, like I said, I'm the lead OSS engineer at Coiled. As part of that, I help sort of maintain and grow the Dask ecosystem, just helping extend Dask into other projects and kind of keeping the lights on from a maintenance perspective. And also on the sort of Coiled side, increasing accessibility to scalable computing. So let's start with the first section, which is just Dask itself. So in a nutshell, Dask is a Python library for scalable computing. That's sort of the high-level one-sentence summary. In particular, it's designed to scale the existing PyData ecosystem. So these are packages like NumPy and Pandas and scikit-learn. There's this great ecosystem out there which has really enabled the growth of Python itself, as well as lots of work in the scientific computing space. However, they were not originally designed with scalability in mind. So Dask adds a scalability component to these existing libraries. It's also flexible enough to accelerate custom workflows. So whatever particular code you already have laying around, you can use Dask to parallelize that code. It's also designed to work on a single machine, so I can use Dask on my laptop. It also scales out to across large clusters. So the nice thing about that is you can use Dask both to maybe prototype things on your laptop, working with a small data set, kind of doing proof of concept. And then you can use the same system. You don't have to change your tool set whenever you scale out to maybe a full data set for your full sort of processing workload. Dask also has a rich, active community. It's a totally open source project. It has a BSD license. It's a NumFocus fiscally sponsored project. It's an open source project. It's an open community project. It's open to public contributions from the community. It's also open to ideas, importantly. And it's actively developed alongside lots of other projects in the Python community. So Dask maintainers are also maintainers of NumPy and Pandas and scikit-learn and Jupyter, and the list goes on. So it's really developed as part of the surrounding ecosystem. So when I talk about Dask accelerating the existing Python ecosystem, so I'm also going to assume, let me know if this isn't the case, I'm going to assume you can see my mouse too. I'm going to use my mouse to point at things. Let me know if that's not the case. So we have NumPy, we have Pandas, we have scikit-learn. I'm just going to assume people know and love these packages. So we can do NumPy operations here. We can do our ND array operations here, where we're doing some sort of vectorized computations. We can use Pandas to read in CSV files and do some data analytics, do some group by reduction operations. We can use scikit-learn to train machine learning models. The Dask versions of these look very similar. So I'm going to kind of toggle back and forth between these slides, so you can pick up on the API changes. They're very similar. There is a Dask version of NumPy called Dask Array. There's a Dask version of Pandas called Dask Data Frame, and there's a Dask version of scikit-learn, which is called DaskML. And the APIs look very similar. We can just deal with larger than memory data sets in all these cases. Like here, for the Pandas example, instead of reading in a single CSV file, like we would with Pandas, with Dask we might read in a whole directory full of CSV files. We those all into a single data frame object. The way these Dask, I'll call them Dask collections. That's what I mean when I refer to the Dask array and the Dask data frame, all these different data structures. Those collections are made up of, in the NumPy array case, a Dask array is actually a chunked multidimensional version of NumPy. So a Dask array is actually a collection of lots of smaller NumPy arrays, and we'll process those NumPy arrays independently, only working on a few at a time. For the for the Dask data frame version, a Dask data frame is actually made up of a lot of smaller Pandas data frames. So for those who don't know, Pandas deals with tabular data sets. So we have like an index and a bunch of columns, like rows and columns, and Dask data frames are partitioned along the index. So in this example, it's kind of hard to see, but the text here says January, February, March, etc. You might have a data set where each month has some data that is a Pandas data frame, and then you can sort of glue those all together to get a much larger data set, which is a Dask data frame that wouldn't necessarily fit into memory on a single machine. Dask will work on those individual partitions to lower the overall memory burden for computations, to allow you to extend Pandas to larger than memory and distributed situations. Let's maybe dive in a little bit deeper, looking at, in particular, the Dask Array API. So generally speaking, Dask APIs, so Dask Array and Dask Data Frame, the code will look a lot like NumPy and Pandas. And under the hood, what happens is they generate task graphs, which are shown like, here's the user code, and here's the corresponding task graph on the right. So you can see here, we use Dask Array.ones, which is analogous to NumPy.ones, to create an array which has 15 elements inside of it. Remember, Dask arrays are chunked versions of NumPy arrays. So this just tells you how many, what the size is of each of the chunks. So the entire array has shape 15, has length 15, and the chunks will each have shape of 5. So I'm going to have 5, 5, and 5 are the chunks. So I'll have 3 chunks altogether, and then I'm going to go ahead and create the sum of that array. So what you can see here is these circles represent functions that are called, and these boxes represent like the output of those functions, and sort of the flow, the control flow here is represented by the arrows. So you can see I'm going to call, what this ends up actually doing whenever we compute this Dask array, this Dask computation, is it calls NumPy ones 3 different times, once for each of the partitions. We then individually, for each of those partitions, get the sum. We call NumPy sum on those partitions. We then call sum again on the result of all those sums for the individual partitions, and that produces the overall sum for the entire Dask array. So this is called blocked algorithms. Like, that is what is kind of backing these Dask collections. And this example is relatively straightforward. It's kind of a map reduce type style. We're applying some operation, in this case sum, and then aggregating with another sum in this case. We can start building up more complex expressions. So this is just taking the sum of an array. We can also take an array and add itself to its transpose. So I can take like NumPy ones, create a 2-dimensional array this time. So now this array has shape 15 by 15, where the chunks are made up of little 5 by 5 arrays. And then I can take this array X and add it to its transpose using a very familiar NumPy syntax. That task graph is starting to look a little more complicated. We don't need to go into the details here, but like maybe if you squint your eyes, you can see like here are kind of these shorter versions are like where the diagonals in this matrix where we're taking its transpose and adding itself to it, adding its transpose to itself are happening. You know, we're taking like a chunk in that array and we're taking its transpose and adding it to itself. And these larger ones are kind of the off diagonal where we're actually doing that operation twice. The nice thing is that you don't actually have to worry about these block algorithms. They're implemented already for you in Dask. And these can get, I don't want to say out of hand, but you can do some complex things, right? So you can create an array, you can add in a matrix multiply, you can add in a sum, you can subtract the mean, you can take standard deviations, all the good, goodies that you're used to with the NumPy API, you can do with Dask, and it will generate some complex looking task graph for you under the hood. You don't have to worry about generating this graph. That's done for you. Dask's schedulers, whenever Dask actually goes to compute these graphs, it will do so in parallel. So we'll talk more about that in a little bit. I'll just say that the Dask APIs generate these task graphs, and then Dask goes and sort of crawls through that task graph and computes things in parallel where it can. Let's go ahead and look at an actual example with some code. So I wanted to point people to,
Could I hop in really quick for a clarifying question?
Yeah.
Ivan in the chat is asking, you had that example where you said the chunks are 5 by 5. How do you know that 5 by 5 is good?
Yeah, that's a great question. So generally speaking, there's going to be some trade-off between, the chunk size that you're actually using and the computational resources you have. So like Dask, when it's computing, when it's doing this and going through that task graph, I'm going to use some words that will kind of make sense later on, but whenever a Dask worker node is actually computing things in this task graph, it will actually need to load a few of these chunks in at a time. So in general, it's good to have the chunk size be such that it can fit a few, a handful of chunks into your worker's memory. So I'm kind of touching on some topics we'll revisit later on, but that is sort of the short answer to your question. Is you can tune the chunk size to your particular available computational resources. So hopefully that answers your question. You should feel free to circle back later if that doesn't. So I want to point people to examples.dask.org. This has a bunch of interactive examples through Binder that are contributed from Dask users. So I'll go there. Let's see what happens to my screen. Cool, it went to it. There are a ton of examples here. There are some basic examples about arrays, data frames, machine learning, and then there's some more domain-specific applications here. So handling imaging processing and ETL pipelines with prefect, for instance. Each one of these links here, so we're first going to look at the array example. Each one of these links will have a rendered Jupyter notebook here that you can just kind of read through. If you'd like to run through this notebook, you can click Launch Binder here. What that will do is spin up a pod somewhere automatically for you to run that notebook, and it also spin up a software environment that you'll be able to run this notebook in. We already have a built image for this repository, so this will take about a minute-ish to actually spin up. It's currently launching the Jupyter server now. So here's that link to the actual example we're going through if you're kind of following along at home. Great, our server is ready. Thank you, Binder. It's launching things for us. Great. So here is that notebook that I was referring to for Dask arrays. I'm kind of going to fly through this notebook a little bit. This is more just to give a sense and kind of a flavor of what working with Dask looks like. We're also going to totally ignore this cell. I'm going to execute this. We are going to come back to this cell later in the talk. For now, let's let this leave your mind. Here is some Dask code. So we're going to import Dask array as DA. That's kind of the convention, just like we have import NumPy as NP. And here I'm going to generate some random Dask array. This has a similar syntax to NumPy's random.random function. Here I'm just choosing 10,000 by 10,000 random array. That's the size. The chunks individually are 1,000 by 1,000. Dask arrays have a nice HTML wrapper here. So we can see the task graph that underlies this particular array. There's 100 individual tasks that need to be executed here. The entire array itself is 800 megabytes in size, so that can actually fit in memory. This is more just kind of illustrative. And the individual chunks are each 8 megabytes in size. We can then do all the sort of things we're used to. So here I can use my NumPy syntax. I can say y equals, I can take this random array x, add it to its transpose. We can see now that we're building up that task graph. So now I have 300 tasks in my task graph. I can then, Dask arrays, much like NumPy arrays, support slicing, supporting, reduction algorithms like mean, and you can specify axes and things like that. At the end of the day, I get some value out, or some Dask array that I actually want to compute. None of what I've done so far has actually triggered a computation. Everything I've done so far is kind of setting up that task graph that gets built up, and then to actually execute that, you call compute. So that's one difference between NumPy and Dask, is Dask is lazily evaluated. And at the end, you can say, I have the thing I want, I've set up the computation I want, I'm going to call compute. Dask, you can go off and compute things. So Dask has a Jupyter Lab extension, which I'm going to attempt to use here. That will give us some good insight into what's going on during our computation. So this is a bouquet application here. And let's see if this is set up to work. I'm going to call compute here, and we should hopefully see some tasks starting to fly around. Yeah, so that first cell that I said to ignore, that was kind of setting all of this up. You can see now I'm processing things, like here's a random sample, that's one node in the one function we're calling in that task graph. Here is a get item. There's a bunch of things happening, and you kind of saw a nice progress bar down here. That helps give us some good insight into the computation that's happening, and in the end, I get my result. This is actually just what it's returned is a concrete, good old-fashioned NumPy array. But I should also say, for those who are interested, Dask works with where the individual chunks that are wrapped inside the Dask array, they can be NumPy arrays. It also supports other array types. They can be sparse arrays if you're dealing with sparse data. They can be CuPy arrays if, for instance, you are doing some GPU accelerated workflows. But yeah, this was all just to kind of get a sense and a flavor for what actually using Dask looks like. I highly recommend checking out other examples on examples.dask.org. Okay, switching back to slides. Not all problems will fit nicely into the array and data frame API. So that's kind of all we've been talking about so far: Dask array, Dask data frame. Those are what we call those are like high-level interfaces. Dask also implements low-level interfaces that let you parallelize custom algorithms that don't fit nicely into the array and data frame workloads. So this is sort of just a skeleton here, this code on the left. This is just to get a sense of something you might actually encounter in real life. I have some function f, I have some function g. They maybe take in some inputs, return some outputs, and then I have some code down here that then does stuff with those functions. Here we're looping over some data, we're calling our functions f or g depending on the values I'm looping over. The specifics of this little example are not actually important. The main takeaway here is that this code actually doesn't fit nicely into the array or data frame paradigm. So this is a custom algorithm which I would like to parallelize. There are opportunities for parallelism here to run different calls to this f and g function at the same time. So one interface Dask has is a Dask delayed interface. This actually lets you build up that task graph manually with just slight modifications to your code. So I'll maybe toggle back and forth between these two. You can see on the left-hand side as I toggle, the main differences here are that I decorate my functions, f and g, with this Dask delayed decorator. And then at the end, I call compute. Because what we're doing here is much like in the array in the data frame case where we lazily build up this task graph. That's what we're doing here. We're just doing it manually. And then at the end, I want to actually compute my result. So I will tell Dask to go ahead and compute this task graph, but do it in parallel where you can. Let's actually, what we're doing under the hood is building up that task graph and, like I said, executing it in parallel. Let's go ahead and look at an example now, going back to examples.dask.org. So there is an example also that walks through exactly what I just showed, that delayed interface. I'm going to choose a slightly different example here, just because it will highlight a couple extra points. This is the Dask's futures interface. For those who are familiar with Python's concurrent futures API, Dask implements a superset of that. So as you'll see in a moment, futures, the future notebook is here. Great. So again, here's where I'm kind of setting up my Dask cluster. We'll revisit this shortly. But for now, I'm just going to execute that cell and kind of ignore things. So down here, I have a few functions I've defined. inc, double, and add, and they do kind of what you expect them to do. Inc will increment its input, double will double it, and add will add those two inputs together. I've added a sleep in here to kind of simulate some real work being done. Like basically a time delay that you would expect with some real function that's actually performing some kind of computationally intensive thing. We can run these functions locally, like so, or we can actually submit those functions to be run on our cluster in the background. So what happens here is instead of just running inc1 in my current Python session, I can say, hey, Dask cluster, go ahead and run this. I can use client.submit to submit this increment function with these inputs. You just do function, and then you can pass in args and quargs to that function and return a future. That future current state is pending. That just means it's kind of pointing to something that is going to be run on the cluster in the background. And actually, your current Python session and your cluster will constantly communicate with one another, and eventually this task will finish. So we can see now when I print the future, its status is actually finished. That means it's done, the computation is computed, it's being stored on my cluster. Let me know whenever you would like to retrieve the result of that computation. I can retrieve this result by calling result on this future. And I get back the result of this increment function on with an input of 1. I get back 2. You can use this same, you can submit functions with inputs that return futures. You can also then take those futures and use those as inputs for other tasks which you submit to the cluster, and that helps you build up these task graphs much like you would with the Dask delayed case. So here I submit increment, then I also submit my double function with some inputs, and then I add x and y. Those are the futures for my increment and my double. So what this is going to do is actually set up a dependency here. I should actually be able to maybe visualize that. Oh, no, I can't. Never mind. What that's doing is that's going to create a future where it's going to create a task. You want to add x and y, but x and y are futures. So it's going to create a dependency saying, I can't actually compute this add until x and y are done. So it will wait for those two x and y computations to finish, and then it will take the results and pass them into the add task. You can then get the result of that by calling result at the end. You can also do, this allows you to do lots of many things, lots of interesting things. You can submit lots of tasks. So maybe now I'll pull up the dashboard again so we can start to see some of these tasks that are being submitted, see them get executed. So there is our task stream. Great. So let's go ahead and start submitting a bunch of tasks. So now here I have a for loop. I'm doing all these tasks I'm submitting. I'm now going to scale up my cluster. I'm going to scale my cluster to provide me more workers because I'm thinking things are going a little slow here. I want to speed up my computation. You can see initially I had 4 workers, and I just scaled up to having 10 workers, each with 4 threads. Now my computation is going by a little quicker, and eventually it's done. Progress has stopped. Like I now have my result. So like down here, if I wanted to get that result, I could do total.result. Yeah. All these tasks up here, I set up some large computation. This is the final result. You can do interesting things. I am maybe going to hold off here and go back to the slides. I recommend going through the rest of this notebook if you'd like, or checking out other notebooks on examples.dask.org. Okay, back to slides. So that was sort of the high-level overview of Dask as a project. We have these interfaces, Dask Array, Dask Data Frame. We have high-level interfaces. We have low-level interfaces, Dask Delayed, Dask Futures for customizing custom workloads. I now want to talk about deploying Dask. We're kind of going to circle back to that cell at the top of those notebooks that I just executed and said forget about. So what a Dask cluster looks like is roughly this. There's 3 different types of components to a Dask cluster. There's a client. This client lives wherever you happen to be running your code. If you are running a Python script, you create a client in that Python script. If, like in those examples I just went through, I'm kind of running through a Jupyter notebook, I create a client in that Jupyter notebook. That client object is like the user-facing entry point to a Dask cluster. You use the client to submit tasks to your cluster. The cluster itself is actually composed of a single centralized scheduler. This receives the tasks from the client that you submit, processes them, computes a bunch of state. It determines what dependency, what tasks depend on other dependencies. Are there any resource restrictions? Like did this task you just submit, like, do I have to run that on a GPU, or can I run that on any worker with a CPU? It computes a bunch of state and then submits those tasks to worker nodes. So there's the client, the scheduler, and the workers. And the workers are where the tasks actually get executed. That's where we are actually running that add function and that increment function that I had in the previous notebook. So deploying a Dask cluster involves basically spinning up these scheduler, worker, and client processes. This is actually relatively straightforward to do this. There are several ways to do it. I'll show one right now. So I'll switch over to terminal. Over here, I'll maybe increase my font size a little bit. I have Dask installed. I'm going to launch my scheduler process by just using the Dask scheduler command line interface. That's going to launch a scheduler. It's going to have some output here as it's spinning up the scheduler process. And it tells me my scheduler is at this address. I'm running this locally on my laptop. I've spun up a local process here. I'm going to then, over here, launch a Dask worker that connects to that scheduler. So I'm going to pass in that scheduler's address. That's all I do. I say Dask worker and then point to the scheduler address. It connected to it. I'll do that one more time. So I'll have 2 workers in this cluster. Let me do Dask worker again. So now what I've just done there is I've launched a scheduler process on my machine, on my laptop, a worker process, a second worker process. So that's sort of everything in this dashed box here. I'm now going to create a client that connects to that scheduler. So I'm going to, in this case, I'll just like launch IPython, if I can spell it right. I will, from dask.distributed, I'm going to go ahead and import that client object that's in this diagram here. That client lives there in Dask. I'll then create my client. So to connect to this running scheduler I have over here on my laptop, I'll just pass in its address. That's all I have to do. So now I have my client here. You can see here's my 2 worker process. They each happen to have 8 threads. This is like the total memory in my cluster. I can then import Dask array as DA and like do all the things that I just did before on the cluster. This cluster happens to be running locally, so I can do like da.ones, 10, and I can say the chunks are, I'll have chunks of size 2. I can do things like x.compute. Like that's a pretty simple computation, but it worked and it executed on my cluster. It executed on these 2 workers I just spun up. So that's one way in which, that's kind of the low-level way in which you can spin up Dask. I'm going to go ahead and close down this worker, and this scheduler. Let's just actually get rid of these tags. In practice, this is not the experience that users tend to like. So what a lot of people do, if I can spell IPython right, is Dask, in addition to the client, also has a local cluster object. If I can import things correctly. And so instead of going through and kind of manually launching scheduler and worker processes, Dask clusters tend to be deployed using what are called cluster managers. One such cluster manager is this local cluster. So I can say cluster equals local cluster. I can say I want 5 workers, number of workers, and I want each worker threads per worker. I want each worker maybe to have 2 threads in it. I've encoded some state about the workers that I want, and there's my cluster. It spun up for me. What just happened there was exactly what happened before when I went into my different tabs in my terminal and launched a scheduler, launched a worker, launched another worker. That exact same thing happened here. It just is in a much better and more approachable API for people, basically. This also has some nice methods, like I can scale things. So like I started out with 5 workers. I can scale up to 10 workers. All that's going to do is, so now you can see I started with 5 workers, I scaled, now I have 10 workers. That just launches, 5 more, in this case, worker processes for me. So that's how you would launch a Dask cluster locally here. There are these cluster managers for a wide variety of different types of systems that you would like to potentially deploy a Dask cluster on. So this local cluster is just for deploying things as the name describes, locally. There are lots of other, go back to presenting, lots of other projects for deploying on different types of hardware. So we just talked about this one. I'm linking out here to the documentation page for all these different projects. Also, this list is not totally exhaustive. So there's a Dask Kubernetes project, which, much like sort of the local cluster object, has a kube cluster and a Helm cluster for deploying Dask on an existing Kubernetes cluster. There's Dask Cloud Provider, which supports sort of all the major cloud provider platforms. You can launch things in AWS with EC2 clusters and Fargate clusters, and GCP with a GCP cluster, and Azure with the Azure VM cluster object. These are all kind of similar in spirit to the local cluster. It's like, give me a Dask cluster on GCP, for instance. There's Dask Job Queue for more traditional HPC systems. There's Dask Yarn for like Hadoop, traditional Hadoop type clusters. These are all great projects and are really a testament to the Dask ecosystem that these exist. You can today launch Dask on virtually any type of hardware you would like to launch Dask on. However, in practice, we see that there are additional needs for using Dask effectively in a team. So like when I say anyone, I mean anyone who knows about Kubernetes or knows about cloud providers or knows about these HPC systems, who has some domain knowledge or is willing to learn those things and is okay sort of spinning up hardware or spinning up infrastructure. So you either have access to or have the wherewithal to spin up a Kubernetes cluster or launch things on GCP or on AWS, you know how to provision things like IAM roles with the right permissions, things like that. Oftentimes we find that actually all the things that go along with deploying Dask can be prohibitive for like a data science team, say. And we find that there are often feature requests for, or rather, not feature requests, the things that teams need to do to effectively use Dask. We've seen lots of patterns there. Dask maintainers have seen that managing software environments is incredibly important. That's like the first hurdle people usually run into. Making sure that your software environment that you have locally is the same one you have remotely on your Dask workers. Managing Kubernetes, managing authentication. There are lots of levels of authentication, but managing that, like for instance, making sure that your Dask workers have the same, say, AWS S3 credentials that you have locally so they can access the same data sets. Setting up logging infrastructure, TLS certificates, cleaning up idle clusters. That's super important. You don't want to leave a cluster up over the weekend not being used and kind of like have those resources tied up and get charged for them. Having GPU support, supporting user quotas, so certain users have certain resource restrictions. I highly recommend, and yeah, there's like ... There are many things needed to use Dask effectively in a team. I highly recommend checking out Matt Rockland's Hosting Dask talk, which I linked to here from PyData Global 2020. He walks through some of these different aspects of deploying Dask clusters. In particular, he kind of focuses in on the user's journey for deploying something with Dask Kubernetes and what it takes to actually do that. You can, but it does require knowledge of Kubernetes, basically. That brings us to deploying Dask with Coiled. So as I said, Dask maintainers saw several common patterns around deploying Dask in production, which are listed here. These are sort of the things people often want and either don't know how to set up or don't have the resources to set up or do have the resources to set up, but maybe their DevOps team is actually better served working on other problems and not just maintaining their Dask cluster. So we decided, some of Dask maintainers decided to form a company, Coiled, around making it easy to run Dask clusters on the cloud or other infrastructure. The overall goal is to launch Dask clusters for you. Thanks to work from Dustin and other PyPI maintainers, you can, in fact, pip install Coiled, and these two lines will get you up and running with the cluster with Coiled. There's a lot of other things we can do with Coiled, but this is sort of the hello world of Coiled. So now I'm going to maybe switch to a quick demo just to kind of give a flavor of what it looks like to use Coiled. So here I'm running locally on my laptop here, right? So like I am just on a Mac doing some stuff. I'm going to launch Jupyter Lab here locally again. And I'm now going to spin up a Coiled cluster. So I'm going to import Coiled, and here I'm actually, instead of spinning up 10, I'll spin up 30 workers real quick. So much like when I did use Dask's local cluster, this is spinning up a scheduler, and in this case, 30 workers for me. But in this case, they're not actually spinning up all those processes locally. They're spinning them up for me on AWS, sort of in the cloud for me. Everything is being taken care of. I don't have to worry about setup networking. I don't have to worry about setting up TLS certificates or logging infrastructure. Coiled is kind of taking care of all that stuff for me. While that's spinning up, this takes like a minute or two roughly, because it's actually provisioning resources on AWS. While that's happening, I'll maybe jump over to cloud.coiled.io. This is sort of the web interface for Coiled. Here we can see this is a table of all my clusters. I was running some clusters earlier today. This cluster right here that's pending, that is the cluster that I just spun up in this notebook over here. You can see it will give me some cost estimates, how much this cluster will cost me sort of at a rate, like how much per hour, as well as the total cumulative cost as well. While that cluster is spinning up, I'll say Coiled does a few other things that address those pain points that we talked about. The main pain point, or not the first pain point we see people run into is software environments. Coiled does provide mechanisms to easily build and manage software environments for you so that you can use both the same, say, Conda environment on your Dask worker and locally. You can like point Coiled to, say, a Conda environment file or a pip requirements file. It will generate a Docker image for you that you can use on your cluster. So like, here was me doing some GPU imaging stuff. So I'm like installing CuPy and scikit-image, for instance. You can also manage these. You can view them, you can delete them, you can share them with colleagues if you'd like. There's also lots of other nice features like managing accounts. So like this particular Coiled account has lots of other, this with all my coworkers in it. You can provide core limits, you can add members, you can remove members. This is all to share the same infrastructure. My cluster is probably spun up by now. Let me refresh. Yeah, it is. Great. So my cluster is running now. So I'll go back over to my notebook. You can see that took just under 2 minutes. It took 2 minutes. So that's typically what we see. These spin up times are somewhere around 1 to 2 minutes, which all things considered is seems to be within users' pain tolerance. I'll then create that client again. I'll connect my local Python session up to this remote cluster in AWS. And now I'll use the task stream again, so I can get a sense for what is going on in my cluster. So I'll like maybe look at the task stream. I'll look at the progress bar if I can find it. Where is it? There it is. And then I'll maybe also look at my workers. There's like a nice little workers, there we go, thing. This just gives you kind of a snapshot of what your workers look like. I spun up 30 workers. You can see there's like a line. Each worker is displayed here. You can see the current CPU and memory usage. It's nice to have. And then here, I'll just do some Dask workflow. At this point, now that I've spun up a Coiled cluster, I have access to all of the Dask things that I would normally do. So here I'm using Dask data frame to read in some remote data set. So you can see all the read CSVs happening. This data set happens to live in AWS. This code should look very familiar to Pandas users. I then do some group by aggregation, and that was it. For reference, I think this data set is something like 20 or 30 gigabytes. It's a little bit bigger than the memory I have on my laptop. This is actually not like a, Dask will work on terabyte data sets easily. This is still technically out of core computation or out of larger than memory. This is still a larger than memory data set for my laptop, which is where this Jupyter session is running. Yeah, maybe that was it. I just want to kind of give a light Coiled demo just to get a sense for things. Let me go back to presenting. And yeah, references now. So I'm linking here out to some other places where you can learn more about Dask and Coiled. So here's the Dask documentation. There's an awesome Dask tutorial at tutorial.dask.org. It goes through in much greater detail a lot of the things I just touched on. Highly recommend it. If you like to learn through like sort of group tutorials, there's lots of, or rather like conference style tutorials. This tutorial's been presented at SciPy and PyCon in the past, so just go on YouTube, you'll be able to find a video. There's also Dask examples, which we've already looked at. I highly recommend going through all those great use cases. So that's for Dask. And then for Coiled, you can sign up for the Coiled beta at cloud.coiled.io. It's totally free. you can use up to 100 cores concurrently. That's sort of the limit for the free tier. There is a paid tier, but there will always be a free tier for Coiled. And then yeah, docs for Coiled are at docs.coiled.io. And with that, I will say thank you everyone for your time and for having me. I appreciate your attention. Are there any questions people have?
Yeah, so thank you so much for your talk. That was really good. There have been a little bit of questions and a little bit of chat over in the chat window about like thread level parallelism versus process level parallelism and where Dask sort of fits in those paradigms. Maybe I could ask you to speak to that a little bit.
Sure. Yeah. I'm sorry. I'm going through the chat now. Can you repeat the question again?
Yeah, just about the difference between thread level parallelism and process level parallelism and where Dask fits in that distinction.
For sure. Yeah. So there's definitely a trade-off. So like there are some trade-offs there in terms of like serialization of tasks. So if you're doing multi-process processing, I guess, you have to, they don't have a shared memory space. So you have to actually serialize some data if in one process, if another process needs it. You should actually have to serialize it, send it to the other process and deserialize it. There's some overhead associated with that. That doesn't mean that the multi-threading workloads are the solution to everything, because there you have other issues like Python guild contention, for instance. Dask supports both of these types of workloads. So a short answer is each Dask worker is its own process, and each Dask worker has a thread pool that it runs tasks into. So you can have cases where you have one worker with 1,000 threads. That's kind of an extreme example. Or you can have 1,000 workers, each with one thread. And you can have everything in between. Oftentimes we find that workloads are somewhere in the middle. So you'll have a certain thread pool size on lots of different workers. It seems to be a good balance for balancing like things like guild contention and serialization, but at the end of the day, it depends on the particular workload you're doing. So hopefully that answers the question.
Yeah, I think it does. There's another one that's just come up here in the chat. And if you are someone in the audience and you have a question, you can, of course, feel free to unmute yourself and ask it yourself. If you don't want to use your own voice, I'm happy to read them for you. Lucas Smith asks, are there any major pros or cons of Dask versus PySpark?
Yeah, so that's a great question. There's a lot to unpack there. So I'm going to maybe share my screen real quick for just a second. And I will direct you to, if you go to docs.dask.org, and then go all the way down to the bottom. This is actually one of our most visited pages. And then you do, where is it? Comparison to Spark. There is a detailed thing here. There are many pros and cons to when you would want to use Dask or want to use Spark. And much like the threads and versus processes case, it depends on your particular situation. There are lots of concerns. Like if you're on a Python team, you might want to use Dask. If everyone knows Java or you're used to working in the JVM, you might want to use Spark. There's also questions about ecosystem, age, and trust. Spark is much older than Dask. It has a lot more momentum in that way, and also like it is more, I guess I would say, like real world tested than Dask. Not that Dask isn't used in large deployments in production, but Spark has been around longer. Scope, internal design, I'd recommend looking at this documentation page. The answer is generally, it depends. There are some technical reasons to prefer one over the other. Oftentimes we find people are using them for other like social reasons. Like maybe you don't like PySpark tracebacks enough, and so you switch over to Dask. Maybe you are used to using scikit-learn, and so you would use Dask instead. There are also lots of reasons to choose PySpark.
Yeah, like I did use Spark, and I was talking to the main guy that actually built Spark a while ago, and my main complaint was that Python wasn't like the first class citizen in Spark. Like we had issues where like we had to like when you look at the logs, you would see like some of the JVM logs, and then you would see some Python logs, and it's like very confusing which one should you actually go by. And
that's a common pain point people have with PySpark who are used to a sort of native Python experience.
Yeah. So I would say I haven't used Dask, but my experience with Spark, well, using Python in Spark was the fact that like Python didn't feel like was like the main, as I said, like first class citizen there. It was something that was added because it was Python was popular, but And I talked to Matej Zaharia a couple of years ago at the conference, the Spark conference, and he promised he's gonna do a lot more, but I don't know if he did it. So maybe this is one more reason maybe to use if you're a Python developer, maybe Dask might be maybe a good choice.
Yeah.
Right.
Excellent. Thanks for answering that question. We have another one here in the chat from Jenny, who says, you showed how some scikit-learn algorithms, such as logistic regression, are implemented in Dask. To what extent can you reuse the scikit-learn code here versus rebuilding them from the ground up? And I assume she's asking about the estimators themselves.
Yeah, great question. Maybe I'll should just keep sharing my screen. But yeah, so I'll direct you to ml.dask.org. That's the documentation for the Dask ML project. And you're totally right. Some of these estimators have been rebuilt to work with Dask arrays and Dask data frames instead of scikit-learn, which works with NumPy arrays and Pandas data frames. That allows you to keep the same API while still using larger than memory data sets. That being said, if I can find it, here we go. Scikit-learn actually integrates with joblib under the hood. So like whenever you're using a scikit-learn estimator or like say a grid search or something like that, anytime you see the in-jobs equals parameter floating around, what that's doing is dispatching to joblib to run things in a process pool or a thread pool somewhere. Well, somewhere's on your local machine. Joblib itself, this is like one of the great sort of powers of like integrating different projects in the PyData ecosystem. Joblib itself, which integrates with scikit-learn, also integrates with Dask. So you can use the same exact code, but instead of telling joblib to run on local threads and processes, you can tell joblib to farm out tasks to your Dask cluster. So there may be an image here, there may not be. Oh, okay, it doesn't look like there is. But basically, looking at the snippet here, all of this code should look exactly the same. Like this is the scikit-learn load digits utility. Here we're using an SVC model. We're going to then do a grid search, randomized grid search for that model over this given parameter space. Normally you would do something like, fit in jobs, 10 or whatever, or in jobs -1 in a lot of cases, to like have this instead of dispatched locally, dispatched to your Dask cluster. All you need to do is wrap that in this context manager. This is how you tell joblib to use the Dask. It's called the parallel backend for joblib. This will then run things on your distributed cluster. It will run all the grid search like trials on your cluster. This is just one example of a way in which you can directly reuse scikit-learn code. There are other cases as well. There are also, I should maybe circle back, there are some cases in which you can't. There are some models, and that's why we have rebuilt some of those estimators, like logistic regression, have our own Dask implementation of them that work with Dask arrays. But there are certainly use cases where you can just reuse good old-fashioned scikit-learn code and have it run on your Dask cluster.
Thank you so much for that. We have a question from Sherry who wants to know if you might increase the font size in your browser a little bit.
Absolutely. There you go. Sorry about that. Any other questions?
So we have also always beginners here. People kind of forget about this. They think they want to show videos. Now, if you want to start with Dask, one of the first things is you have to set your mind in doing things in parallel. Are there any nice tutorials about how you take a serial program and transform it into a parallel one and use Dask to run something?
In fact, there are. So I would highly recommend going to tutorial.dask.org. The link
Can you show us one? Just show us one.
I can take you to tutorial.dask.org. Sure. Introduction. For instance, parallelizing code with Dask.delayed. This is kind of a more in-depth version of the delayed example I went through quickly. And maybe to your point, more importantly, it has a lot more prose here. It explains things in more detail than I had in this 30 minutes. So you can see here's an inc function, an add function. It just has a little more prose as to here's the serial example, and then here's how we go ahead and actually parallelize things with Dask delayed decorator, for instance. Hopefully that's to the point you asked about.
Yeah, that's good. This is the direction. Now, when they wrote the code already, and now they want to deploy it. and let's say that they do it on their own machine, how many processes they can parallelize? Think about it, someone who's beginner, who's doing it for the first time. What should they do?
How many processes can they use on their machine?
You have to, how many workers should we use?
Oh, sure. So I think there may actually be a relevant section in the tutorial for that as well. I think it's over here in distributed. Yeah. So by the way, here's to the earlier question where someone asked about threading versus processing. Here's sort of a little sentence and some other sections that talk about that. The answer is you should experiment, and it depends on your particular problem. Unfortunately, there's not like a great answer for this problem. For all your problems, you should use, I'm making up a number here, 10 threads or 5 threads and 10 processes. Unfortunately, it's just not that simple. So throughout the tutorial, I think we typically fix things to a certain. We actually just end up calling compute, which will detect how many CPUs you have on your machine. That's often a good starting point. If I have 4 cores on my machine, start with 4 threads or 4 processes and kind of work from there. So maybe back to your original question, a good starting point would be the same number of, say, CPUs you have on your machine.
Good, so now I'm walking the stuff as if I was a beginner. So now I ran my first code, and after I ran my first code, sometimes it works wonderfully. I wrote some more complex program, and now it tells me all sorts of things about the Python is not good or things like this, which happens quite a bit. So, for example, I didn't include the library, and I want to make things speed up.
Yeah.
What should I do? Where should I look?
For that, I would recommend checking out Coiled. Like I said, this is one of the first pain points people run into is managing software environments. You installed a library, you installed S3FS locally to read your data, but you don't have it on your workers. So I'd recommend checking out Coiled for that.
Okay, so you recommend if you go and need some service, then check out Coiled. Is what you're saying? Okay.
Yes.
Excellent. So we have some more questions that are coming up here in the chat.
Sure.
P2K Piece Under would like to know if there are any use cases for using Dask with smaller sized data sets. So maybe something that could fit in the memory of a single machine.
Yeah, that's a great question. When dealing with small amounts of data, oftentimes, so basically if you're using a small data set, Dask has a really convenient API for parallelizing custom workflows with Dask delayed and the futures interface. So there, it's nice. That's more where it's not so much the size of the data that is kind of constraining you. It's more the amount of tasks, kind of the CPU. You're more CPU bound is the term used for that. So Dask is useful in those situations. If the question is more, I have a NumPy and Pandas-like workflow, but I can fit the data set into memory, the answer there is then definitely don't use Dask. You should use NumPy and Pandas wherever you can. Adding distributed computing, while Dask makes it easy, is definitely you're adding additional complexity on top of the problem. So if it's like an array or a data frame workload and you can fit things into memory, then by all means use NumPy and Pandas. If it's a custom algorithm you're trying to parallelize, then use Dask. Hopefully that answers the question.
Yes, they say, understood, thank you so much. We have another question. This is from Greg Freeman. Greg would like to know more about the free tier on Coiled.
Yeah, that's a great question. So I'll maybe start by saying the free tier, we're currently reevaluating the free tier. There will always be a free tier. What I'm going to say now, since it's being recorded, may be outdated a month from now. So just with that asterisk, I'll tell you about the free tier today. Today, you can sign up for Coiled, and it is so there's a paid version of Coiled and a free version of Coiled, and they are both there is complete feature parity between there. There's not you start to pay for Coiled and you get new features. it's not like that. It's all about usage. So for the free tier today, you can get 100 cores running concurrently. That's sort of the limit of the total resources you can use in the free tier. If you want to go beyond that, that's where we then enter the paid plan. So anyways, that's the case today. Hopefully that answers your question as well. There's like other things that Coiled also does, which are more like enterprise support, which we're also happy. I'm happy to talk about that as well. But in terms of like talking about the free tier, that's what the free tier is.
So say that I was interested in enterprise support from Coiled.
Yeah.
What does that look like?
Yeah, so we do a whole variety of things. Like the short answer, and this is maybe going to be too short, is like you should contact sales@coiled.io, and then yeah, we can like have more conversations. But what the enterprise support will get you is what you can obviously you can pay for the resources that you use. We also offer Dask expertise, so that can take many forms. That's why it's kind of a vague answer. That could be getting people up to speed on Dask. That could be setting up some custom thing for your particular use case. Like if you're on some exotic hardware somewhere, we can help spin up Coiled where appropriate. Yeah, so just general support and expertise is sort of what is in the enterprise tier.
Excellent. Thank you for answering that. Yeah. Were there other questions that people had for James?
Awesome. Well,
all right.
Thank you so much for having me.
Well, thank you, James.
Thanks so much.
Appreciate it. All right, so I'm stopping the recording now. We'll stick around, and we'll talk on various topics here. So stopping the recording right now.